les derniers arrivent. On vous attendait pour commencer. Okay, good morning. So I'll be talking in English because I have some colleagues in the US who wants to listen to me or look at this presentation, which I have been discussing with them for some time. So present myself, Jean-Dominique Polack. So I am a professor here, and I'm teaching normally acoustics, most specifically room acoustics, and this is the origin of this interest for generalized formulation of acoustics. Can also say that a shorter version of this paper will be presented, I hope, to the next French conference on mechanics in Brest next August. So here is the outline of this paper. So it will be very mathematics, even though the introduction will show you where does the question come from. And I will probably dwell mostly on the examples because it's nearly half of the presentation. So where does it come from? It comes from a paper from Janowski and Spanduk, if I speak English, German properly, which showed experimentally show the curvatures of rays above absorbing surface. They were interested. They were the first one. Spanduk was the first one to build anechoic chambers, and he had a very low ceiling place. So he put a lot of absorbing watts. So it was made of material which could burn, so he was very careful in the design. And he looked at the propagation of waves at grazing incidence. And the results he found was that the waves were decreasing in energy much faster than what was expected with the direct sound. So he build these experiments, which we want to reconstruct here. Here is the absorbing material. It was made of layers of sheets of absorbing watts, which were standing in the vertical direction. He had a very directional loudspeaker, so it's high frequency, basically, and 2 microphones. And the idea is, he's sending pure waves, and he's moving the top microphone, so distance between the 2 microphones is something like 30 centimeters, and he's moving the top microphone in order to get annulation of the signal. And when he gets annulation of the signal, he reckons that the wavefront will be traveling through the two microphones. So this is the plot of what Spanduk measured, so it's 20 hertz, but 200 hertz, but I think he was using higher frequency. The parameter is the height of the loudspeaker. So the higher the loudspeaker is, the more the higher the loudspeaker is, the more direct would be so put it in the other way. If the loudspeaker is very low, then you would be at grazing incidence, and when you raise the loudspeaker, then the incidence will gradually increase. So this is the plot of the angle difference between the direct sound, the direction of the loudspeaker, and the perpendicular to the plane where the 2 microphones are located. And you see that when the difference of angle is small when the loudspeaker is very high, and can be very large when the microphone, the loudspeaker is very low. So at grazing incidence, you get a very strong angling of the wavefronts inside, which falls down inside the absorbing surfaces. So Kremer and Müller were able to confirm that. They used the general reflection formalism, what happened above a surface of a specific admittance beta, and then they, by adding the incident and the reflected wave, and doing the development, they were able to get this equation, which show that the wavefront equation will be given by a term proportional, so there is a term proportional to x and proportional to psi. Psi is the real part of the admittance. It means that there is real part, means that must be absorption. This is responsible for absorption. And the explanation they give is that if there is no absorption, so there is no net flow of energy going into the surface. So you need absorption to measure it. Actually, the first one to observe that was Beccesi in the 30s, and he was linking it to what is called seat effect, the fact that when you're sitting in rows in a concert hall or in the theater, then the grazing incidence will be much more absorbed than what you would expected. A second idea behind, second reason for looking at this question was a paper by Carsten Bo Rasmussen, who was interested in computing with boundary element method the propagation above not one, so a plane not with one admittance, but with two different admittance. So here is you have the first admittance or impedance in this case, and the second one, and he was not able to get something working with a boundary element method unless he used the artifact of putting secondary sources or virtual sources above the discontinuity and applying Huygens principles in order to reconstruct the field at the receiver from the sum of all these sources. So when you think of what it means that the ray here having two reflections must be in fact curved above the surface. So that was a second reason for looking at that. And it means that just using the traditional acoustics was not working. Then there is a third reason, which is the papers that Hugo Dujourdet and myself have been publishing in the last years, where we compute energy in corridors and open space using the energy trace tensor formalism. And there we use Adhoc boundary conditions, which are actually the absorption coefficient, incident intensity is proportional to total energy, and scattering, which was grazing intensity reduced by something we call tangential stress. But when we tried to apply it to more generalized conditions, then we found out that we couldn't really extend this condition. So you can find this absorption and scattering coefficient by using the energy distribution function à la Boltzmann, for example, but and using spherical harmonic expansion to compute the field just above the boundary, but it couldn't be extended to the fact when you had generalized coordinates. So what we were looking and what I'm looking at by this question is to try to find the natural with inverted comma, boundary conditions that would generalize what we know in acoustics. So we start with a general wave equation. As I told you, it would be very mathematical. So we used this time-space, four-dimensional time-space with a metric tensor, GIG, and we used the traditional what is called Einstein convention. That's when you have an index up and down, then you have an implicit summation of the index, which are repeated only if one is an index and the other one is an exponent. So the traditional, it's called the metric tensor because you get the distance from, or the elementary distance from the tensor elements. The volume is also given by the determinant of the metric tensor. The determinant is negative in this case because we're in space-time. And the generalized wave equation, which I use the D'Alembertian sign, is just using the secondary derivative. But here we are using covariant derivation, with respect to the variable which are xi, and gig up is the inverse of gig down. So they are not exactly the same. What is covariant derivative? So it's not the same as partial derivation because it takes into account the changes of the basis vector orientation. It means that when you move from one position in space-time to another, the basis vector do not have the same orientation. So you have to take into account the fact that they will rotate, so they will have coordinate in the other direction. And this is measured by the Christoffel symbols. So don't go into details how the Christoffel symbols measure this rotation. And of course, in the original direction, there will be a shortening of the vector. But the vector do not also have exactly the same length, even though we have, so it can be very general. So for a function, there is no difference between the covariant derivation and the normal derivation, just because there is no basis vector involved. For a covariant tensor, then we have one term here. And if we have a tensor of rank 2 like GIG, which is contravariant, then we have two terms, one for each of the indices which involve these Christoffel symbols. Notice that there is a difference for covariant and contravariant tensor, which is the difference of sign. So what is important, I won't go into more details, is that covariant derivation commutes, so we can invert the order of the deltas here, or triangles. Covariant derivation commute with the metric tensor. That means basically that the covariant derivation of any covariant derivation of the metric tensors is identically null. So that's a very important property, and this is used to define the contravariant derivation by just inverting GIG here with the DIG. So to come, what I forgot to write is to transform tensor from its covariant form to its contravariant form. You just multiply the index you want to transform by this matrix GIG. Reciprocally, when you want to convert by the other matrix, the reciprocal matrix. So if we apply that to the product of the D'Alembertian of the potential, velocity potential multiplied by the complex conjugated of this potential, then we can, due to the fact that for the wave equation the D'Alembertian is 0, then we have an identity. Using the differentiation rules, we come to this equation here, which is just the fact that it's 0. We developed here just normal derivations formula. And then we can say that the two terms here are equal to 0. Then we can separate it into a real and imaginary part. And the real part, when we carry out this, we found out that this term is just twice the Lagrangian, and the imaginary part, just to the fact that this part is real, then the imaginary part would be 0. So it means that we can define two quantities, something which I call the 4 velocity, which is equal to this real part, or this real part here, and a 4 vector potential, because we'll see it's the analog of a vector potential in electromagnetic, which is due to which is the imaginary part of this quantity here. Why do I call it a 4 velocity? It's because it's by analogy with the what we know from fluid mechanics. We know that the divergence of the velocity will account for the volume deformation. And here we know also from that the Lagrangian accounts for the volume deformation of the time space. So this is why I had called that 4 velocity. But we won't use it very much. More interesting is, and what I was looking for, is the conservation of the stress energy tensor. And this conservation is obtained by, instead of considering the product of the D'Alembertian with the complex conjugate of the velocity potential, we look at the covariant derivative of the velocity potential. So there's a little bit of mathematics, but basically it is the same. And actually it's amounts to what is, it's an application of Noether's theorem, which, as you may remember, is the mathematical form of the notion of invariant conservation law in physics. So I won't go into the details. The only thing you have to notice is that here we have used the fact that you can invert or change the order of the covariant derivative. And here we have used the definition of the contravariant derivatives. So that's explaining this term. And then when we apply that, then we can also look at a real part and imaginary part. We get that the real part is the derivative, covariant derivative of a quantity. We recognize the Lagrangian. We'll see it later on. And then the imaginary part has the quantity we get has no real meaning here, so we just call it JK, and we'll see later on by analogy with electromagnetic that this is a current, a 4 current, by analogy with electromagnetism. So if we look at energy conservation, we introduce the symmetrical energy stress tensor as the real the real part of this quantity, so this where it's the product of, so it's a tensor, it's a covariant tensor, which is the product of the velocity elements, if we, so dj phi by the so the quadratic product of the velocity elements, components, but of course using the fact, since we have complex potential, then we have to use complex conjugate. And then by applying what we suppress to this, the second term, the term we had here, in order to get what is known in the literature as the stress energy tensor. So the idea is just to get the contravariant derivative of the stress energy tensor is equal to 0, because as I didn't point out here, we take out no, what do we? No, the term important here is the k. So we, in order to get it here by multiplying delta I GIG will give us the contravariant derivative multiplied by this GIG will give us the covariant derivative with respect to coordinate J. So that's the idea. So these elements, this conservation of energy in acoustics was already given by Morse and Ingard in '68, or even earlier, and Morse and Feshbach 10 years later, they used it, but not in the acoustical context. And so they give the elements that the name which are given by Morse and Ingard. So the reduction T is just a Lagrangian. We have the total energy density is the first element, the upper, the first element on the diagonal of the stress energy tensor. The reactive, the active acoustic intensity are the element, all the elements on the first line except the first one. So they are, A is here 1, 2, or 3. or reciprocally because it's a symmetrical tensor on the first column. And the rest of the elements, where A and B takes the value 1, 2, or 3, are called wave stress. It's called wave stress tensor by Morse and Ingard. I don't know where they got the idea from wave stress, but I think it's because it looks like a stress tensor in vibration or something like that. They do not give any account of it, and they never used it to anything. In their book from '68, Theoretical Acoustic, each time they have a wave equation, they write this, the conservation of the stress energy tensor, but they never use it to anything. And that was actually what attracted my attention when I started with that, working with Hugo some years ago. So what is more surprising, and really surprised me, is the fact that if you look at the antisymmetric part of the stress energy tensor, which is not formally correct because the stress energy tensor is by definition symmetrical. But if you look at the equivalent imaginary part, then you find that it's satisfied Maxwell equation. That was really a surprise. So we start with an anti-symmetrical tensor, which is defined by something which generalized the rotational of the four-vector potential we have defined earlier. So here it's the computation of the derivative of the covariant derivation. So we have the two terms. When we subtract them, we get the definition of Fig. So we recognize the imaginary part associated to the stress energy tensor. It means, of course, that there is no diagonal elements because in the diagonal it vanishes. And then what comes out of that, because of this definition, is that this tensor, the antisymmetric tensor Fig, naturally satisfied generalized Maxwell equation. So we recognize here the equation we have written earlier, which is that the contravariant derivative of Fig is equal to the current, what I defined as a 4 current. And then there is a more something which is, when you look at the definition here, it corresponds to the divergence of a rotational. So we know that the divergence of a rotational is 0. So this is just due by construction. The second equation comes by construction. And it's explicited here, because if you replace Fig by the value we give here, we see that all the terms here, knowing that we can change the order of derivative, all the terms come once positive and once negative. For example, this one, which is positive here, is negative here, and so on. So there, naturally, we get a 0. And these two equations are actually the generalized formulation of Maxwell equation. So what does it mean? So I also written here the current, the conservation. Why is it a current? It's because when we derivate it once more, we compute the contravariant derivative of this quantity, then due to the construction, by construction, it will be equal to 0. And this is the definition of a current, so that in electromagnetism. So that's why I called it a current. So I won't go into the details. So if we now look at what it is and try to give physical meanings to the different element of this tensor Fig, then we find out that the elements on the first line or on the first columns are just the reactive acoustic intensity, what is called known in acoustic as the reactive acoustic intensity, and therefore the other elements, which where you remember that the diagonal of the other elements is zero, is identically null. I call it the reactive wave stress, because the corresponding real part was called wave stress tensor by Morse and Ingat. So as I said, this came really as a surprise that we could recover the Maxwell equation. And so I haven't really looked further into this, but this is one of the things I want to do in the next few years, because I've been on that for something like 3 years now. So now we go back to the generalized wave equation, and we try to solve it on a 4-dimensional manifold. We call, as traditionally, the border of the manifold, we call it the surface S. We still have the metric tensor, the volume element, but we now considered a surface admittance condition on the surface, which I write this form. It implements the velocity. This is the elements of the velocity. So the admittance must be, as the velocity is a covariant tensor, the admittance must be a contravariant tensor, otherwise we cannot build the scalar product. And since it is a boundary condition, we put 0 on the end. So what are the element beta I? We will develop them later on, but they are complex. I call them complex for admittance, and they are, as traditionally, built with a real part and an imaginary part. The notation I use here is the one from Morse and Ingat, so I kept their notation. So in order to find the equation, normally, traditional way is to find the extremum of the Lagrangian, which I've been writing here. And when you find here, that's what I call the velocity, 4-velocity vector. And I integrate it on the whole volume and try to find the maximum by inverting the order of derivative. But what is interesting is that I'm using this identity, which defines the covariant derivative of a contravariant vector, by just using the normal partial derivative of the contravariant vector multiplied by the volume form. And then I apply Stokes' theorem to transform the volume integral to a surface integral. And what I'm interested in is to introduce the velocity on the boundary and the conjugate velocity on the boundary. So the way to solve this is to introduce or to choose the local coordinate on the surface so that and to choose to choose the metric tensor on the boundary, so that the product of the metric tensor multiplied by the outgoing vector will give the complex admittance. And then when we have that, if this is equal to this quantity, and we admit here there is one supposition, but I do not have, no, not really here. No, if I take that and write it as the real part of the admittance, it's the real part of the admittance, then I can replace it here by the real part of the admittance and write a little bit more further. So here, the top one is the real part. So I have separated again the real part and the imaginary part. The idea is to write here this as psi, and psi is the difference between beta and sigma. We have to take into account that it's not exactly the same here. We have the covariant. No, we have the covariant derivative of the complex conjugate, it must be the complex conjugate of beta. So we get here a difference of sign between the imaginary part, and when we, as we know that this is 0 because this is the definition of the impedance, we just get an imaginary part, and we can show that the sum of the Lagrangian over the whole volume is equal to a boundary integral of this quantity here. It's the imaginary part, so it's actually the vector potential multiplied by the imaginary part of the admittance. So if we consider that the admittance purely real, then this vanish, and this is what we will do in the following in order to solve in the, particular cases. For the imaginary part, we have something very similar. So here we replace it again by beta, and using not beta but psi. It's very similar, except that since we have a difference here, we must have a sum, and then we find out that the sum of the on the surface of the imaginary part of the impedance multiplied by this 4 velocity is equal to 0. Something that was already proven by Morse and Ingard in general acoustics. So far, what did we obtain? We obtained unexpectedly the Maxwell equation for reactive intensity and reactive wave stress. So, and what is the physical interpretation? The physical interpretation is, actually I put it the way around. As we know that the imaginary part or the reactive intensity is linked to the stationary field, I considered that the Maxwell equation will be describing the standing waves and the eigenmodes. As a matter of fact, we do have then quadrature relation between pressure and particle velocity, as is known from eigenmodes. I couldn't resist to compare it to Kaluza-Klein theory. I don't know whether you know this theory, but Einstein worked for 10 years on that. It's one of the historical attempts to unify Maxwell equation with gravitation. But it's introduced a 5th dimension, which no one has been able to find out what it is from what I read in the literature. And here we have Maxwell equation without a 5th dimension, but still need to interpret what is, how do they apply, and can we use them in an interesting mode to look at, to find the standing waves. So, in other words, the local field is described by the energy tensor, and the global field is described by the reactive field, or the Maxwell equation, just because we know that eigenmodes are usually, it's a global way of looking at a space and not a local space. And then, as was proven already in ordinary metrics by Morse and Ingard, global and local fields are coupled at the boundaries. So if we consider that there is no coupling, so what do we get? And these are the example I will be looking at. I'll be looking at 2 examples. The first one is, both of them are actually sound propagation above an absorbing plate. And I will consider this plane as the horizontal plane, and the coordinate and the normal coordinate is x1, and x1 is counted positive upwards, so it's the floor which is absorbing, and we're looking at propagation above the floor, exactly what Spanduk and Jankowski were doing. We reduce the boundary condition to the traditional admittance. That means that we consider that the normal derivative here of the normal velocity is proportional to the pressure with a certain admittance term. So this admittance term would be the ratio of these 2 beta. Here beta is real, purely real, and xi is real. Or if they're not real, they are they have the same, they are proportional. So the outgoing 4 vector going downwards, so that's why it's negative. And the local matrix must satisfy the G, the element here, the first, this element G, JG1 are multiplied by N1 are equal to X1. So that means that we cannot have the traditional Minkowski matrix or a diagonal matrix for the a diagonal metric matrix, but we have non-diagonal terms which are non-zero. This is the major difference. So I will look at 2 cases. So this is the way I write it. And I look at 2 cases. The first one, I consider that this coefficient A, B, and C depends on coordinate x1 only. And the second one, I will generalize the case here. So the boundary condition is, of course, here given. This is the value of G01, and this is G11. So this will be given by xi is B over A. And we normalize it by the product AC plus B2 is equal to 1, which means that we will get a determinant of G with the volume, it's -1. It must be negative, as I said. It's -1 because I have considered that the speed of sound is equal to 1. I've normalized it to 1, as I implicitly did in the preceding part. So in order to be able to write it as xi here, B must be negative if xi is positive. Usually xi has to be positive, so B, the most general way to account for absorption is to say that B is negative. It will have some implication later on. So now just write all the terms, the Lagrangian here. It's not the traditional form, but we see that these elements C, B, and A are playing a role. C with the first phi0 square, derivative square, A with the phi1, and B with the cross term. I do not have the coefficient 2 because here have the two to write the real part, I have to sum with the complex conjugated. Now, computing for the Christoffel symbol is just tedious computation, but you can do it. Then we find out that most of them are equal to 0, except the one here, which, if you look at them, they are only involving the coordinate 1 and 0. There is no involvement of the other coordinate. So when we look at the conservation of the stress energy tensor, so this is more simpler form if we look at TIG with one I contravariant and J covariant, just because if we apply it's because we do not have a formal definition. It's more complex to define the contravariant derivative than the covariant derivative. So it's more interesting to transform it into the covariant derivative of some tensor. All in all, it is the same, because if you move it's basically the same idea, but it's the terms here are no longer, these terms here are no longer symmetrical. And for example, the T00 is negative in this case. It's always negative, so it's not really an energy. So by using the definition of the contravariant derivative, I get the covariant derivative of this quantity, and then applying the definition of the covariant derivative, then I have the 2 term in gamma, and the 2 first can be, as done previously for vector, can be set together. If I look at the normal derivative, the normal partial derivative of TIG multiplied by the volume form. So TIG is now given by the definition here. So there's, in a sense, it's easier because here there is only only on the diagonal element do you subtract the Lagrangian. But all in all, it's the same because the computation becomes complex afterward. So these are all the calculations. As I said, the Christoffel symbol were only involving the coordinate 1 and 0, so there is no influence of the Christoffel symbols on the derivative which are parallel to the surface. It's only normal to the surface and the time derivative. So we found out that's the difference between these two diagonal terms, which is playing a role. They are and we'll see, they are always combined together. What does it mean that there is no no extra term on the parallel derivative? It just means that there is no redirection of energy, and if which is what we expect, if the impedance is constant on the surface, we do not expect to get scattering or things like that. And we'll see that in the next step when we introduce coefficient that depends on the which varies along the surface, then we will get scattering. So there is also a way to compute it on surface. Well, I will go. I intended to talk longer on that, but when I was reviewing it yesterday, I realized there was this equation, which looks much more complex, is basically the same. The only thing I could say is that here you see there's only the x1. Yes, I should have been a bit more explicit. I have renamed the coordinate 0, 1, 2, and 3. So instead of x with an exponent 0, x1, x2, I've used the traditional coordinate, and x index 0 and 1 just mean which planes and which value of this coordinate I've been using. So this has nothing to do with the with what I was using before. So if I write it here, you see that here there is no integral on the plane. This, on the first equation, no integral on the plane x equals 0, x1 is 0 on for the two parallel derivative, just because this, due to the impedance condition, there is the integral would be 0. But for the normal derivative, this is not the case. So we have integral. We have to take into account what happens on the surface itself. But so that was getting a bit complex. So some of the other interesting elements are the Riemann tensor, which is defined here. So it's very tedious calculation. And then the contraction on the two terms here, the first and the second one, the first contravariant coordinate and the second covariant coordinate gives what is called the Ricci tensor. And further contraction with the GIG give the scalar curvature. And when so you can do the computation, and we find out that only these terms in 0 and 1 are non-zero. The scalar curvature is not non-zero. And when you combine them to get the Einstein tensor, which is just RIG minus GR, 1/2 of R with the correct metric tensor, multiplying it to get the two coordinates, then we find that the Einstein tensor is identically 0. So it was just to make the link with the general relativity. What I was mentioning at the beginning, what is the Ray equation here? So the Ray equation, if we apply traditional, for example, characteristic theory, we find that the Ray equation is given by this equation, which is it's in a sense the dual equation to the wave equation, because instead of having a derivative, so contravariant elements, here we have covariant elements, so we have to use the inverse matrix here. And this is also called, if we introduce the notation here, which are the time derivatives, so velocity, this is known as Monge equation. But from there, it's not very easy to find out what is the equation of the rays, especially when B, C, and A are changing. So the best way is to go through the generalized equation, the generalized the acceleration with introducing the proper time, which is just the negative part of the proper as GIG, the metric elements. So this is just using the inverse metric element, and then we use VIR, the generalized velocity with respect to the proper time. So just mathematics using partial derivation to get the acceleration. So we had here the definition of the generalized acceleration. Then we have to do full computation to find out that we can compute the acceleration of each of these coordinates, x1, x2, and x3, as a product of two velocity and something implying the Christoffel symbols. So I have been computing it here for x. So x, remember here, x is the coordinates normal to the surface, and y and z are parallel to the surface. So what happens if we if the rays are parallel to the absorbing plane, then at the beginning, x prime is equal to 0. So all these terms are 0, this one as well, which means that the only term which remains is the first term here, 1/2 of BA1. So remember that B is negative, and A1 has to be positive, because A increase from the boundary to get to 1 at some height above the boundary. So A is lower than 1 at the beginning. It means that this term here will be negative, and then x squared will be bending down. Remember that x is positive when going upwards, so x second negative means that the acceleration is going downwards. So this is what was experimentally observed by Janowski and Spanduk. And if you look at the other case, for example, x prime and z prime equal to 0, then you see that in this case, the ray remains perpendicular to the surface, which is what we were expecting. There is no acceleration normal to the surface. Parallel to the surface. So now introducing varying absorption with the same metric tensor means that A, B, and C are depending on all the coordinates, and the boundary conditions are the same. Everything remains the same. So the Lagrangian will not change. We still get this, I don't remember how many, 8 Lagrange Christoffel symbol, but we get many more here which are non-zero, and this means that the stress energy tensor takes a much more complex form. So what most important thing is that we still get the difference between T00 and T11. T00 is not, as I said, it's not exactly the total energy, but it's related to it. But T11 is something, it's another term. So we do not get really the total energy anywhere here. Then we have terms which I have underlined with purple, and they are terms which will vanish if we choose C equal A, which would be as there is no constraint on the choice of these elements, except the impedance on the surface, we can choose C equal A, which would be a natural choice, and then 6 further elements vanish. So I still have to look quite a little bit what comes out of it, and I haven't been working further on that, but normally that's something we want to do with Eden and Roland later on this year. So if I come to the conclusion, the main results are that we've been constructing a metric tensor with boundary condition, where here the boundary condition, I repeat here, where we have looked at the particular case where these generalized impedances are all real. We have got generalized equation for energy conservation, and we can consider that we have introduced, when you look at that, an adaptation layer between the surface admittance and the free space at some position above this surface. And from what I have been looking at and what I have been presenting, there is no constraint on the thickness of this layer. We can choose the variation of A, B, and C the way we want, as long as we have the only constraint I have been introducing is that the determinant of G is equal to 1, so in absolute value, and the second things, so it's not varying, and the other constraint was to have the impedance, to find the impedance on, or the admittance on the surface. So this is something, the free parameter is something we have to look further on. Then we have been able to demonstrate ray curvature above finite impedance surface. And then, as I said, the big surprise was that reactive intensity and wave stress satisfy Maxwell equations. So what is still to do? So finalize non-uniform admittance on boundary on boundary planes. So numerically solve the equations, as we did with Dujourdi in the last years. Find rule for the thickness of adaptation layers, of the adaptation layer. From what is known from acoustics, we know that you never do measurements, or for building acoustic, you never do measurement within 1/4 of a wavelength from the walls, because you don't get homogeneous, you don't get the same, the pressure is not the same value, it takes a different value from the rest of the room. So it means that probably the thickness of the adaptation layer is 1/4 of a wavelength. That's where we have to look for. So we have to look at ray curvature above. I don't remember what I wanted to say with that. I think it's just this from the last slide. I didn't notice was twice. And then further develop Maxwell equation for reactive intensity and wave stress. But there was one thing I didn't write, is that our equations are not really compatible with classical absorption and boundaries. If I look back on this one, none of the term here is proportional to the absorption, to the total energy in just above at the boundary. So this just means that probably there are some terms which are missing. We have to look for a more generalized admittance, and not only restricted to the 2 first term with I equal 1 and 2 as is traditionally done, but to look at further terms inside, which makes it very, very complicated. Already it's complicated, but I think it's quite, so I don't see really what comes out of that. But I have a look at it. So these are some of the papers which have been. This one was very difficult to get. I found the reference in Kremer and Müller, which is but getting this akustische Zeitschrift from 1937 in France doesn't exist. I had to ask some colleagues in Aachen to get it. And then these are the last. Okay, any question? So oui, tu peux.
Je me demandais dans quelle mesure tu pourrais étendre cela à des systèmes pour lesquels tu as de la dissipation. Ou c'est vraiment quelque chose qui
oui,
est
on pourrait
envisagé dans le cas des problèmes d'acoustique.
On pourrait, mais j'ai pas regardé.
Ah.
Le problème de la dissipation,
parce que là, ça portait en partie suite des droits de conservation.
Oui, j'avais regardé, mais l'un des problèmes dans la dissipation, c'est, sinon on peut le regarder ici, c'est d'introduire le Lagrangien devient compliqué parce qu'il est. Alors Morse a utilisé ce qu'il appelait les fonctions bi-orthogonales, qui est une construction où il prend. On s'aperçoit quand on a la dissipation, effectivement, alors bon. En acoustique des salles, on néglige la dissipation à travers dans l'air, on ne la met que sur les bords. Donc il y a effectivement de la dissipation, puisqu'il y en a sur les bords. Mais quand on veut introduire la dissipation, ça devient compliqué. Alors il faut que je me rappelle de mes souvenirs. C'est parce que il n'y a pas une forme aussi simple pour le Lagrangien. Pour le définir, il faut définir un état conjugué. Cet état conjugué est en fait le complexe conjugué du potentiel des vitesses. Et donc, Morse s'était dit, je multiplie par le conjugué de l'état, alors je n'aurais pas dû l'appeler, c'est l'état dual plutôt que l'état conjugué. Il y a un état dual. Donc, je multiplie par le conjugué de l'état dual, mais l'état dual étant l'état conjugué, ça revient à introduire au lieu de valeurs absolues, on supprime les valeurs absolues. Alors, il y a eu plusieurs publications là-dessus, en particulier Jean Kergomar et Denis Matignon ont repris ça il y a quelques années. Puis ça me chagrinait parce qu'on n'a plus aucune équation, on ne peut plus montrer l'existence ni l'unicité de la solution. Et j'ai été très content de découvrir en cherchant, parce que j'ai eu à reviewer il y a quelques années un papier qui utilisait ce formalisme. Alors j'ai été regarder dans la littérature si on ne trouvait pas quelque chose là-dessus, et j'ai trouvé dans le journal d'optique des gens qui avaient essayé de faire une décomposition là-dessus, en utilisant, qui montrait que ça divergeait très vite. C'est-à-dire que les premiers termes convergent et après ça explose. Parce qu'il n'y a pas tout simplement parce qu'on peut arriver à mettre ça égal à 0 sans que tous les termes soient positifs. Voilà, donc on peut arriver à...
Ok, merci.
Donc c'est plus compliqué. Déjà c'est compliqué, mais c'est plus compliqué. La question que j'aimerais poser, est-ce que je suis pas toujours très certain de la qualité de mes calculs. Est-ce que vous avez vu des erreurs? Bon.
Ouais,
je suis pas toujours très rigoureux, donc il y a peut-être des erreurs.
Sur la slide 25, à la ligne 2, il y avait.
Est-ce qu'il y a des erreurs? Oui. Non, j'en ai retrouvé. Oui, il y en avait une là que j'ai vue, que j'ai pas vue. Encore, j'en ai retrouvé encore. Ça, j'ai oublié de le supprimer quand j'ai fait le copier-coller. Je l'avais pas vu. Pourtant, j'ai relu hier. D'autres questions? Non. Merci.